It turns out that these two intersect in the octant where capital A, B, and C are all positive. So if they're all positive, then we can convert both of these in terms of arithmetic mean and quadratic mean. Now, how are we going to do that? So simply divide by 3 on both sides the first equation, get the arithmetic mean, and the second equation and square root both sides to get the quadratic mean. So if you do that, you end up having a plus b, capital A plus b plus c equaling 2, and capital A squared plus b squared plus c squared over 3 square root also equaling 2. So if the arithmetic mean and the quadratic mean both equal the same result, that can only happen according to the ladder of means theorem when all three values are equal. And if they all add up to 6 and they're all equal to 2. But wait, capital A is equal to a plus 1. So that means a itself is equal to 1. So you get a equaling 1, b equaling 2, and c equaling 2. Alright, now in this problem, we need to find out the maximum value of n for which this number 17 to the 88 minus 1 over 2 to the n is a natural number. So, of course, no one would want to compute 17 to the 88 and have to subtract that by 1 to figure out the result. So what I did was break this down even further into separate factors simply by a difference of two squares. I got 17 to the 44th plus 1, 17 to the 22nd plus 1, 17 to the 11th plus 1, and 17 to the 11th minus 1. So let's take a look at the first three factors that we actually end up with by breaking it down. So how are we going to prove? How are we going to find out the maximum value of n? Well, let's see what happens if we divide 17 by 4. You get a remainder of 1. And similar to how we did the first problem, whenever you have 17 raised to a power, according to the binomial formula, every term is divisible by 4 except for 1. So since you have 1 at the very end, you're going to have, whenever you have 17 raised to a power and you divide it by 4, you will always have a remainder of 1. So now that you're considering that, if you add 1 to each of those terms, you'll leave a remainder of 2 when you divide it by 4, meaning that it's not divisible by 4, but it's divisible by 2. And that means the maximum value for 2 to the n would be 2, meaning that the maximum value of n for each of those terms, each of those three terms, would be 1. Okay, now let's look at 17 to 11 minus 1. You cannot really break that down any further, so what we can do is, by using the decomposition formula, we can break that down in another way. So since you have 17 to the 11th minus 1, or 1 to the 11th, you can use the decomposition formula by subtracting the bases. In this case, you'd get 17 minus 1. And then the second factor, you'd be adding up, there'll be n number of terms, because there are n minus 1 number of a terms, and you have an extra term. You have a total number of n terms. So if the bases are both odd numbers, and you're just trying to figure out, and you're having like 11 terms of odd numbers being raised to powers, you'll end up with an odd number. So here's where I'm going with this. You have 17 minus 1, and you have an odd number factor. So that means you have 16 times an odd number factor. So, and what is 16? 16 is 2 to the 4th. So if 16 is 2 to the 4th, the maximum value for n, for 2 to the n, would be 4 for this term. So what your final result will be is, you have 1 for the first three terms, and you have 4 for the last term. And since you're multiplying the numbers, all you need to do is add the exponents, and you'll get 7. So 7 will be your answer here. That'll be your maximum value of 2 to the n for that to be a natural number. Okay, now let's go on to this problem. So if a, b, and c are natural numbers, how will we prove that a plus 2b plus 3c, or 2a plus 3b plus c plus 3a plus b plus 2c are not all three odd simultaneously? Here's the way that you can think about it. Each of those numbers have even number addends. You have 2b in the first one, you have 2a in the second one, and you have 2c in the third one. So regardless of what a, b, and c are, you have an even number in each of those terms. So if you think about that, you'll have 8 cases to prove for A, B, and C being even or odd. So if there are 8 cases, they're all going to work the same way. So if we take one case, we can get similar results with the other ones. So here's how I proved it. Let's assume that A is even and C is odd. Let's assume that. So if A is even, you'll have an even term here for A on the first equation. You'll have this first expression, and you have an odd term for 3C. Then regardless of what B is, you'll have an odd number because 2B is by itself even, and you have an even and odd term being added up. Now for the second term, what will B need to be? Because if A is already even and C is already odd, you'll end up having an odd term. Well, you need to have B be an even number because you already have an odd term and you want to get an odd result. So B has to be an even number, so for that to be true. Okay, so now we got our final values of which is even, which is odd. You got A being odd, B being even, and then A being even, B being even, and C being odd. Well, if A and B are both even, you get an even result, and 2C is even at all times because regardless of what C is, so that last one is even. So not all 3 of those terms can be odd, and this is a trial and error process, and the other 7 cases will lead to similar results. So this proves that not all 3 terms can be simultaneously odd. And let's go to this problem where we need to figure out the last 2 digits of the quotient of 7 to the n plus 1 plus 4 times 7 to the n plus 17 when you divide it by 11, considering that n right here is a multiple of 4. So how are we going to do this? Well, let's first simplify the value of 7 to the n plus 1. So if you break that down, that is the same exact thing as if you were to say 7 times 7 to the n. And if you add 4 times 7 to the n to it, you get 11 times 7 to the n. And if you divide the whole thing by 11, you get 7 to the n plus 17 over 11. So let's look at 7 to the n. So if n is a multiple of 4, well let's let n be 4a. Let's say n is 4a. So if it's 7 to the 4a we're talking about, then we're saying 7 to the 4th to the a. And where a is actually a natural number. So what is 7 to the 4th? Well, we all know that 7 to the 4th is 2401, and that is just when a is equal to 1. What if a is another natural number? Well, whenever you're like squaring 2401 or like cubing or any of that, you'll always end up with the 1th digit of 1, and you'll always end up with the 10th digit of 0 whenever you raise it to a power. And so when you think about that, well, if you even just looking at the multiplication 2401 by itself, you'll end up with 0 and 1 being the last 2 digits. So okay, well, if 0 and 1 are the last 2 digits, are we done? Nope. Because you still have 17 over 11. And what is that? You have 1 plus 6 over 11. And 6 over 11 will lead to a remainder. So we just look at the quotient itself. You got 7 to the 4a and you have 1. So if 0 and 1 were the last 2 digits of 7 to the 4a, you just add 1 and you have 0 and 2 being the last 2 digits. Alright, let's go back to a previous problem that I previously skipped. So let's prove, so right here, we need to prove that 3 to the 2012, the 10th digit is an even number. So here's what we can look at. If you raise 3 to powers just by looking at examples, well, you'll see that all the numbers have 10th digit being even. But why? Why is that true? I mean, the 1th digit is obviously 1, 3, 7, or 9, but the even number, the 10th digit apparently is an even number. Well, here's why. If you have 1 times 3 equaling 3 and 3 times 3 equaling 9, what if you multiplied 3 by 7 or 3 by 9? Well, you get 21 and 27. And if you continue multiplying that by 3, you'll just have to, all you have to do is just add the tens digit, the even number tens digit by multiplying 3 by that even digit, and you just have to add it to the number of 21 or 27 to get an even tens digit. So if that's the case, well, if all the powers of 3 have tens digits, that's an even number. Same works for 3 to the 2012. All right then. Thank you.